The plan today is to try and make some sense of molecular orbital theory. Now, in molecular orbital theory, covalent bonds are the result of atoms combining their atomic orbitals to make new molecular orbitals. Let's start by having a look at our little molecule hydrogen, H2. Each hydrogen atom has got the electronic configuration 1s1, so they've each got a 1s atomic orbital, and that's what we're looking at here. So molecular orbital theory predicts that each hydrogen atom is going to combine those two atomic orbitals to make a new molecular orbital, and their bonding electrons go into this new molecular orbital. This is known as a sigma bonding molecular orbital. Bonding molecular orbital, often written as MO for short. And you can see that the electron density is greatest between the two nuclei. So essentially that's what our covalent bond is. That is what's holding our two atoms together. Now, this particular bonding molecular orbital is the result of combining our atomic orbitals in phase. So what do I mean by that? Well, we need to remember that atomic orbitals are wave functions. And like all wave functions, if we were to combine two waves, we could either combine them constructively or destructively. So this is a constructive interference pattern for two waves. So if we assume that each of these individual waves is the wave function for our 1s orbital, and we combine them constructively, we get a bigger wave, which equates to our sigma bonding molecular orbital. Now, if we can combine waves constructively, we can also combine waves destructively. And when that happens, we get a destructive interference pattern, even destructive interference pattern. So when hydrogen combines its two 1s atomic orbitals, we end up making two molecular orbitals. We end up with our bonding molecular orbital, our sigma bonding molecular orbital with electron density greater between the two nuclei. And by combining the wave functions in an out of phase or destructive way, we also end up with a sigma antibonding molecular orbital. And you can see here that when we do that, molecular, it kind of says molecular, you get the drift. When we do that, you can see that actually we've now got a point where there is reduced electron density, reduced wave function between my two atomic nuclei. So what does that mean in terms of bonding for molecules? Okay, so at this point it's easier to have a look at this on a molecular orbital energy level diagram, and I've got a skeleton of one just here. So if we start with our two hydrogen atoms, each of them has a 1s atomic orbital, and when they combine their 1s atomic orbitals to make molecular orbitals, we end up with a sigma bonding orbital and a sigma antibonding orbital, and you can see that that's indicated by the asterisk. So the molecular orbitals, in terms of energy level, we can see first of all that the sigma bonding orbital is of lower energy. It is more stable than the original atomic 1s orbitals were. But the antibonding orbital is less stable. It's of higher energy. Now for hydrogen, each hydrogen had a single 1s electron. So both of those electrons can go into the new molecular orbital. They're going to be spin paired. And hydrogen is going to form a single bond between the two hydrogen atoms. So placing electrons in bonding orbitals contributes to bonding. Placing electrons in anti-bonding orbitals weakens the bond, is one way to look at it. which brings us nicely to the concept of bond order. We can calculate the bond order from molecular orbital theory by subtracting the number of filled antibonding orbitals from the number of filled bonding orbitals. So let's have a look at that for hydrogen. So for hydrogen, I have got a filled bonding orbital and I don't have any filled antibonding orbitals. So the bond order for hydrogen is 1 minus 0, which equals 1. And this corresponds with our idea that between two hydrogen atoms, we've got a single pair of electrons. This is, of course, a Lewis structure, and it predicts a single bond, what we were familiar with. The next molecule I'd like to look at would be a molecule of lithium, Li2. Each lithium has got the electronic configuration 1s2, 2s1. So if we take our two lithium atoms, that would be my 1s, and my 2s at a higher energy level, 2s. I have got 2 electrons for each lithium atom in the 1s, and my 2s orbitals are going to converge to form a 1 sigma bonding orbital and a 1 sigma antibonding orbital. And I've got 4 electrons, so both of these are going to be filled. If we have a look at 2s, well, we've got 1 electron in each. My 2s orbitals, atomic orbitals, are also going to interact to form 2 sigma orbital bonding and a 2 sigma antibonding orbital. Got 2 electrons, they're both going to go into the 2 sigma bonding orbital. So a couple of things I want to pull out of this particular molecular orbital energy level diagram. First of all, when we're talking about bonding, we tend to focus on the valence electrons. They're the ones that are getting involved in bonding, and we can see that here. Because if I look at my 1s orbitals combining to make my 1 sigma and 1 sigma antibonding molecular orbital, then I can see that the bond order at this point equals 0 because I have filled both the bonding and the antibonding orbital. So they don't contribute to the bonding in this lithium molecule. Another reason is because of the greater bond length or distance between the nuclei in my lithium molecule, the 1s orbitals just don't interact all that much. So in terms of bond order, I'm just going to focus on my valence electrons, which have both gone into my 2 sigma bonding orbital, in which case the bond order equals 1 filled bonding. There is nothing in my 2 sigma antibonding, so bond order is 1. So molecular orbital theory would predict that there is a single bond between the 2 lithium atoms in a molecule of lithium. It's interesting at this point to compare the molecular bond in hydrogen with that in the lithium molecule. So a hydrogen molecule, HH, lithium Li, Li, both have got a bond order of 1, which would suggest a single bond within our molecule. The hydrogen bond is the result of a sigma, 1 sigma molecular bonding orbital formed from the combination of 1s atomic orbitals. And in lithium, our bonding is the result of filling our 2 sigma molecular bonding orbital, which is the result of the combination or the interaction of our 2s atomic orbitals. Now, as you can see from these two pictures, a 2s atomic orbital is more diffuse than a 1s atomic orbital. And as a result of that, the electron density between 2 lithium nuclei is less because there is less overlap between 2 2s orbitals than between 2 1s orbitals. The lithium bond is predicted to be weaker, and this is shown with the bond dissociation enthalpy. For a hydrogen molecule, it's plus 436 kilojoules per mole. But for a lithium molecule, it's predicted to be only plus 105 kilojoules per mole. So it takes far less energy to break the bond in a lithium molecule than it does a hydrogen. And just recapping, that's because the diffuse nature of our 2s atomic orbitals are combining in a way that there is less overlap than between two 1s, so less electron density between our nuclei. So what would molecular orbital theory predict for a molecule of beryllium, Be2? Well, each beryllium has got the electronic configuration 1s2, 2s2. So we can have a look here with our 1s and our 1s. These would be each for a beryllium atom, and of course the middle is looking at the molecular orbitals in a beryllium molecule. So I've got 2 electrons in here. We've got our 1 sigma and our 1 sigma antibonding, and each of those would be filled. So as we've seen, bond order would be 0. And if we look at our 2s in each case, so that would be our 2 sigma bonding and our 2 sigma antibonding. Each 2s has got 2 electrons in. So with a beryllium molecule, we would fill both the 2 sigma bonding and the 2 sigma antibonding molecular orbitals. Once again, bond order equals 0. So molecular orbital theory predicts that the beryllium molecule cannot exist because it has a bond order of 0, and this is what we find in practice. Let's move on to have a look at fluorine F2. Each fluorine has got the electron configuration 1s2, 2s2, 2p5. Now we've seen how s orbitals can combine to form sigma bonding and sigma antibonding, but what happens when 2 fluorine atoms combine their p orbitals? Now we're going to have a different outcome. P orbitals have direction in 3D space, unlike an s orbital, which is spherical. And in molecular orbital theory, the z-axis is defined as running along the bond, so in this case the fluorine-fluorine bond, which means that when I bring 2 fluorine atoms together, their pz orbitals are going to be in the right direction or symmetry to interact, and they're going to interact fully. Once again, remember that all orbitals are wave functions, and if they've got wave character, they can combine both in phase constructively and out of phase destructively. So when 2 pz orbitals combine, we're going to form a sigma bonding molecular orbital and a sigma antibonding molecular orbital, and you can see the 2 shapes here. So this was the result of constructive, and this is the result of destructive combination. The px and the py atomic orbitals on fluorine are perpendicular to the fluorine-fluorine bond axis. So when they combine, when 2 px orbitals combine, or when 2 py orbitals combine, we're going to form a new type of molecular bonding and antibonding orbital. I hope you can see in this picture here that we're not going to have a case where a px from one fluorine atom would combine with a py from another fluorine atom, because they have the wrong symmetry. So if we work on the basis that we've got 2 px orbitals, one from each fluorine atom, they can combine in phase. So thinking once again of atomic orbitals as having wave character, we're combining our waves constructively, and we're going to form a pi molecular bonding orbital. And we can see with our bonding orbital, we have got greater electron density between the two atomic nuclei. If we can combine our waves constructively, then of course we can also combine them destructively. So if we've got a pi molecular bonding orbital, we are also going to form a pi antibonding orbital. And once again, in our antibonding orbital, we've got reduced electron density between the nuclei. So what would this look like on a molecular orbital energy level diagram? We're just going to consider the valence electrons. So if this is my first fluorine atom, this would be my 2s, and these would be my 3 2p orbitals. For my second fluorine atom, we have got the same thing going on. And for my fluorine molecule, well, each of my 2s is going to combine to form a 2 sigma bonding orbital and a 2 sigma antibonding orbital. Okay, 2 because we're ignoring the first energy level. With our p orbitals, we've got two different things going on. First of all, let's consider our pz orbitals. They're the ones that can combine more fully, and they're forming sigma orbitals. So we've already used 2 sigma, so this would be my 3 sigma bonding orbital and my 3 sigma antibonding. So they're the result, I make a note of that, these are the result of my pz orbitals combining. My px and my py are combining to form pi bonding and antibonding orbitals. So these would be my 1 pi bonding and my 1 pi antibonding. 1 because it's the first set of pi orbitals that we have got in this molecular orbital diagram. So let's just make a note of those. These two are the result of my px and separately my py orbitals combining. So I've got 2 pi bonding orbitals here and here, and 2 pi antibonding orbitals, and they're degenerate, they're of the same energy. It should also be noted that the interaction between 2 px orbitals or 2 py orbitals is less effective than the interaction between 2 pz orbitals. As a result, the molecular orbital here, the 3 sigma and the 3 sigma antibonding, are more and less stabilized compared to the pi bonding and antibonding orbitals. Right, let's clear this diagram up a little. Let's put some electrons into this. So each of my fluorines has got a pair of 2s electrons. So we're going to then fill the 2 sigma bonding and antibonding molecular orbitals. In terms of the p, we've got 5 p electrons on each of my fluorine atoms. So I'm going to use 2 of them to fill my 3 sigma, always fill from the bottom up. My 1 pi is going to be filled, and my pi antibonding is going to be filled. So all the atomic electrons are now placed in the molecular orbitals that are between my 2 fluorine atoms, these new orbitals. In terms of bond order, well, I have got, in terms of, let's have a look at our bonding orbitals, 1, 2, 3, 4. So it's 4 filled bonding orbitals. In terms of the antibonding, 1, 2, 3. I've got 2 pi antibonding orbitals. So 4 minus 3 equals 1. So molecular orbital theory would predict a single bond between 2 fluorine atoms, which is exactly the same as our Lewis structure. And finally, I would like to take a look at oxygen, O2. Well, we're familiar with our Lewis structure for oxygen. It predicts that we have got a double bond between the 2 oxygen atoms and 2 lone pairs of electrons on each oxygen atom. Now, this Lewis structure predicts that we've got a double bond between the oxygen, but it doesn't explain all the properties of oxygen. One in particular is that liquid oxygen is paramagnetic, which would imply that it's got unpaired electrons. But clearly, when I have a look at my Lewis structure, that doesn't seem to be the case. I've got 2 bonded pairs and 2 lone pairs on each oxygen. So let's see if molecular orbital theory is going to give us a better description of the bonding in an O2 molecule. So oxygen, each oxygen atom has got the electron configuration 1s2, 2s2, 2p4. What does that look like on our energy level diagram? Well, again, we're just going to consider our valence electrons. So I have got 2 electrons in each of the 2s2. So once again, that fills the 2 sigma bonding and antibonding molecular orbitals. So that's oxygen. This is our molecule, my second oxygen atom. And with the 2p, I've got 4 electrons. So 1, 2, 3, 4. 1, 2, 3, 4. So I've got 8 electrons to put into my molecular bonding orbitals. So my 3 sigma is going to be filled. 1, 2, 3, 4, 5, 6, 7, 8. Remember that these 2 pi bonding and non-bonding orbitals are degenerate. So electrons are going to fill 1 pi antibonding orbital each before that they spin pair. So we can see that in the molecular orbital theory energy level diagram, we do indeed have unpaired electrons in our O2 molecule, which would explain why liquid oxygen is paramagnetic. In terms of bond order, well, we've got bonding orbitals 1, 2, 3, 4. So it's going to be 4 minus antibonding orbitals 1. And each of these counts for half because they're half filled. Minus 2 equals 2. So molecular orbital theory would also predict a double bond between the oxygen atoms in O2. If this has been useful, hit the subscribe button, the effortless way to support your studies. And by clicking the link in the blurb below, it will take you straight to the Crunch Chemistry School, where you'll find all the resources you need to get that A-star grade at A-level. Together we can do this.